You want me to discuss assignment 1 with you?
No, teacher.
Huh?
No,
You have
teacher.
not done it, so you don't want me to discuss with you?
No, teacher, not yet.
Okay, it's up to you. Assignment 1 is mainly past year paper. Just want to train you to be ready to answer past year question. Okay, let's try that. To review you, a positive charge ion and an electron enter the respective magnetic field through the slit X. That's your slit X. That's your magnetic field. This is a positive ion. This is electron. Show with an arrow the direction of the electric field, which when applied will enable the charged ion and the electron to emerge from Y. Okay, where's the direction of the electric field in this case? First, determine where is the force on the positive ion for A.
The electric field, okay. Magnetic field is the one going to the right. So electric field means you will be opposite direction, so to the left, right?
You have to determine the electric force, the magnetic force first. Then after that, you have to determine the electric force to decide the electric field. So where's the magnetic force?
Going in.
Okay. So you want the magnetic force going in, then where's the electric force?
Coming out.
Let me just check. Your field.
This for the A, not
For A.
B.
The field is to the right. You know how to read. Right? The positive ion is going up. So the electric force is where? Where's the magnetic force?
For A.
For A.
Going in.
Magnetic force is going in. How come?
Is
it? Let me check.
Yeah, going in.
Right?
Because the magnetic field going to the right, and then the
current. Okay, you're right. Sorry, yes. I'm the one wrong. Okay. The magnetic force is going in, so the electric force was coming out. Remember, the electric force is the one that gives the direction of the electric field.
Yes, opposite.
So correct. Magnetic force is electric force is coming out, so electric field is also coming out. Okay, good. How about B? So you have to show the direction of electric field same as FE, this one. Okay, how about for electron? Remember the dot tell you the electric field.
Electric force coming out, right? Not electric field. Wait, I'm confused.
The magnetic field is coming out. The dot tell you the magnetic field is coming out.
Magnetic field is coming out.
It's an electron. So where is the magnetic force?
Where's the magnetic force for B? Okay. This is coming out actually. Yep, so
the magnetic field is coming out.
Yeah, the field is coming out. Okay.
Coming out. Current is going down. So where's the magnetic force? Yeah.
Going up.
How to go up?
No. So sorry. Wait.
Yeah.
Wait, teacher, the first one, right, teacher, was that the magnetic field was going to the right, and then was that the current is
The current is a moment of positive charge. So electron now is going up. So the current is coming down. Now
so
to
the
read.
force is like going in, right, teacher, for the A.
How to go
Correct.
in? We are not talking about A now. A you have done already. Now we are going to B. Don't get mixed up. B is electron.
Okay,
So the current is going down.
it's a negative charge, so
The field is coming out.
mm, mm.
And see, the problem with you is don't do your homework. Hey, come to think of it, spend too much time on here. Why so long? Yeah, field is coming out. You should be able to point at. Field is coming out. Current is going down.
Current is magnetic field to the right, and current is coming out.
Current is going down. Field is coming out.
Current
So where's the
field is
electric
coming
force?
out.
Where's the electric force? Why take so long? Yeah, field is coming out. Then there's a field. Turn it to you, the field. Turn it to you. Coming out. Then
Yes,
the second finger is going down. Turn your finger going down. Then where's the force?
and then the third finger to the left, right?
Magnetic force to the left.
The force is up. The magnetic force is up.
So now you want the electric force to be to the left, to the right, sorry. Yeah, electric force
What?
to the right. Can?
Wait, just so you try to tell me the first finger is to the left. I thought the third finger is to the left.
The electric force is to the left. Sorry,
Yeah.
magnetic force is to the left. Then your electric force must be to the right. Remember, it's acting on the electron.
Force.
So electric field is to the left. Means the positive plate must be here on the right hand side there to attract the electron. Yeah?
Yeah.
Can?
Can.
Okay. Let's try another one.
Oh, the B thing, right, again. Hello?
Yeah?
Okay. So because the first term is the force, second one
First
is
find the magnetic
field, third one is
force.
current.
Just find the magnetic
Yes.
force. Then after that, the electric force must be opposite, equal and opposite, that's all. And then remember it's an electron.
Wait, so basically that means the magnetic field is going up, lah, right?
Magnetic field is coming out of the page.
Coming out.
You should
No.
know how to read.
What I'm trying to say.
Coming out of the screen or coming out of the page, you must learn to read. Problem with you is you don't do your homework. Then you're wasting a lot of time in tuition. It doesn't help you.
Okay.
Tuition is not a miracle to help you if you don't do your homework. Yeah, why so long? Should be able to twist your finger around. Magnetic force is coming out. That's your first finger. Yeah, first finger coming out. And the current is coming down. Current is coming down. So the thumb should be pointing towards you. Sorry, thumb, your field is coming up towards you. The first finger is pointing towards you. The current is going down. So the magnetic force must be to the left. Yeah. What's the problem?
Yeah, like the magnetic
You should be able to get the magnetic force already. What's the problem? Know how to read. The field is coming out, pointing towards you, the first finger.
yes, coming out for the current, right, teacher?
What coming out of the current? Coming out is a magnetic field. The current is going down, vertically downwards. So your second finger must be going downwards. Then the thumb will point to the left. That's your magnetic force.
Oh yeah. Now I got it.
So you got that, then you can determine the electric force.
Magnetic field is coming out, the current is going down, the force is left.
Yeah.
Current down, force left. Okay. Okay.
Okay, let's go to the next one
Yeah.
then. Yeah, okay. Okay, let's try this one. Singly charged, there is one positive, one electron loss. It's positively charged of the same mass, but different speed enter the region of combined electric and magnetic field between the parallel plate P and Q. Magnitude of the electric field is given. The magnetic field is also given. What should be the direction of the magnetic field in order for the ions of a selector velocity to leave the combined field? So you know the positive plate is here, negative plate is here. So determine the electric force first. Where's the direction of the electric force for the positive charge?
Direction of electric force. Okay. Electric field going up means
You didn't say electric field is going up. You say the the positive ion is moving upwards as all. Learn to read. This is the positive plate, this is the negative plate. So where is the electric force? You can see you are having a problem because you don't study at all. Positive and positive will repel each other, so it's to the right. Electric force is to the right. So the magnetic force must be to the left. That's important to do that, to know all this. Then you can go and determine your direction of magnetic field. So the current is going up. Current is going up. Magnetic force is to the left. So where's the direction of the magnetic field? Direction of magnetic field.
Oh, direction of magnetic field. Okay.
Yeah, direction of magnetic field. Yeah, magnetic force to the left. Thumb is pointing to the left. Yeah,
And
current is going upwards. Current is going upwards.
Magnetic field coming in. Sorry, yeah. Magnetic field coming in.
Okay, magnetic field is going in, correct. Right, first determine the electric force. Positive and positive will repel. That's why you get the electric force. So the magnetic force is to the left. After that, use Fleming's left-hand rule to give the magnetic field as inverse. Correct. And the next part is just use your magnetic force equals to electric force. Right? Don't memorize the formula. Go to the basic there. It doesn't take a long time. Too many formulas to memorize. Right? Electric force formula, magnetic force formula, electric force formula, cancel the Q, and your V is E over B. Take the B down and put in your value, you get the answer. Show the path of the ions with velocity greater than the selected velocity. Where will it go? Yeah, greater than the velocity.
Show the path of ion with a velocity greater than the selected velocity.
This is the selected velocity. If it's greater than this one, yeah.
It goes to the positive plate.
Follow. Look at the magnetic force. Now magnetic force is greater than the electric force, so you must go to the left. Right? Speed of charge determine the magnetic force. So greater speed, greater magnetic force, so you go to the left. Right? It's a curve. Less than the selected velocity. Where would it be then?
To the right, towards the negative charge
That's
plate.
all. Same thing, same reasoning. Okay. Number 4. A beam of electron enters a uniform magnetic field of flux density, this one, at right angle to the field. If the speed of electron is given, what is the radius of the subsequent path? Yeah, given E over M. How to determine?
EVP equals to mv square over r.
Say again.
EVB equals to mv square over r.
Just derive it. Magnetic force. Hey, what am I doing? Sorry, magnetic force equals centripetal force, not electric force. I am also getting back. Not electric force, not electric field. Right? Magnetic force equals centripetal force. Usually don't encourage you, if you can memorize, good, but there's too many formulas to memorize. Always go to the basic. Magnetic force equals to centripetal force, and derive the equation. Right? Your V and V cancel off, there's still got one V here. So the radius, take this one R up, take the PE down, there's still one V here, and put in your value and calculate out. Okay? All right with that?
All right.
Let's go to the, okay, next week I'm going to electromagnetic induction already. Let's go to 16.6. Okay, all voltage in different conductors can be positive, negative, or zero. What can you conclude from these observations? Yeah. All voltage in different conductors can be positive, negative, or zero. What can you conclude from this observation?
Positive Hall voltage implies that the majority of the charge carriers in the conductor are positively charged.
Okay, negative.
Implies that the majority of the charge carrier are negatively charged or free electron.
Zero.
There are equal number of positive and negative carrier in the
Good.
conductor.
Right? Positive charge. If it's positive, hole voltage is basically hole. Positive
More positively
charge moving.
charged.
The carrier is positive. If it's negative, carrier is electron. If it's zero, then it's equal number of positive charge and negative charge. Okay, good. Hole voltage is zero, imply that the charge carrier are equal positive and negative. Okay, good. 2. Explain why the hole voltage produced in a piece of semiconductor is much higher than the hole voltage in an identical piece of metal. Yep, same metal, same size, same dimension as the semiconductor. Why is the hole voltage in semiconductor greater?
Why piece of semiconductor is much higher than identical? Okay. Value of N for semiconductor is much smaller than the N for metal. Therefore, Hall voltage for semiconductor is much higher than that for metal.
What is N? Yeah,
N is the volume. N is the volume density of the charge carrier.
Okay. Right? Basically, we are just using this formula. The P is the same, the I is the same, the E is the same, the T is the same. Only difference is N, correct? Right? Number of charge carrier per unit volume in semiconductor is smaller, greater Hall voltage than metal. Therefore, Hall voltage in semiconductor is greater than conductor. Okay? Okay, let's carry on. Let's do one more. This one. A conductor of dimension A, B, C is in uniform magnetic field of density B. That's your P. The direction of the current is going up. As shown, the charge carrier in the conductor are of positive E and of volume density N. Show the polarity of the hole voltage in the diagram. Yep. Polarity of the hole voltage. Where should I measure the hole voltage in the first place? Yep. Where should I measure the hole voltage?
Hole voltage produced between front and back faces of the conductor with polarity as shown in the figure.
Okay, that's good. And show the polarity of hole voltage in the diagram. Which part is positive, which part is negative?
Positive is the one the upper part is positive.
Are you sure?
Yeah.
Your field is going to the right. your current is going upwards there. Yeah. So if your current is going up, in this case, cannot be in this direction. It cannot be to the right or to the left. It must be either in or out. So how can it be the topmost phase? Yeah. Determine the magnetic force as usual. Magnetic force, where is the magnetic force? Magnetic field is to the right. Current is going up. So where's the magnetic force? Right? Magnetic field is to the right. Current is going up. So where's the magnetic force?
Magnetic force. Okay. The field is coming up. The
field is moving. Magnetic field is going to the right. The current is going.
Sorry, current is going up. Current is going up. Yeah, current.
Where's the magnetic force?
Going in.
Okay, right. So that is the way to decide where is across the front and the back. The front and the back surface. Okay,
Yeah, so the force is going in, right?
Yeah. So it's a positive inside, negative outside. Okay, good. Derive the expression for whole voltage produced in the conductor. Right, same. Start with magnetic force equals to electric force, where the steady state, that means the current is constant, and put in your formula, get your velocity, and then convert your electric field to your whole voltage, V over B, right? Whole voltage from there. So that is your thickness B. Then after that, from this, right, from your I equals NEAV, where is A? A is where the current comes. That's a cross-sectional area, must know how to read. So area is B times your C. And then from this equation, get your V. And then the two V are the same. Put them equal. Equals to V, B, B. And then from there, you can calculate your whole voltage. Can?
Can.
Okay, we'll stop here for 5 minutes. Anything else you want to ask?
No.
If not, you stop for 5 minutes. Then we'll carry on.
We are going to go new chapter, right?
No, not going to go new chapter. We're going to focus. Try some question there. Only next week I'll go into new topic.
The next week Saturday.
Next week is Wednesday, 1 more hour.
So the Wednesday you start doing chapter 6, right?
Yeah. No point in going too fast.
Okay.
You are already lost.
Yeah.
You never do your homework. That's a problem. You cannot go fast. Okay, I'll stop it now. Take a break.
Well, anyway, teacher, because of the physics class in the school also, right? You know what I'll do, teacher?
Yeah.
Because the school teacher, right?
Yeah.
He actually doesn't record the classes. I don't know why.